Gilbert Cell. Our study of differential pairs reveals two important aspects of their operation. One, the small signal gain of the circuit is a function of the trail current, and two, the two transistors in a differential pair provide a simple means of steering the tail current to one of two destinations. By combining these two properties, we can develop a versatile building block. Suppose we wish to construct a differential pair whose gain is varied by a control voltage. This can be accomplished depicted in figure A, where the control voltage defines the, as you can see in this figure, A simple VGA, B two stages providing variable gain. Tail current and hence the gain in this topology AV is equals to V out by V in varies from 0 if ID3 is equals to 0 to a maximum value given by voltage, headroom limitations and device dimensions. This circuit is a simple example of a variable gain amplifier VGA. VGAs find application in systems where the signal amplitude may experience large variations and hence requires inverse changes in the gain. Now suppose we seek an amplifier whose gain can be continuously varied from a negative value to a positive value. Consider two differential pairs that amplify the input by opposite gains, figure B. Now we have V out 1 by V in is equals to minus GM RD and V out 2 by V in is equals to plus GM RD, where GM denotes the transconductance of each transistors in equilibrium. If I1 and I2 vary in opposite directions, so do mod V out by V in and mod V2 mod V out 2 by V in, mod V out 1 by V in and mod V out 2 by V in. But how should V out 1 and V out 2 be combined into a single output? As illustrated in figure A, the two voltages can be assumed producing V out, and V out 1 plus V out 2 is equals to A1 V in plus A2 V in. Figure A, summation of the output voltages, summation of the output voltages by two amplifiers. B, summation in the current domain. C, use of M5 M6 to control the gain. D, Gilbert Cell. Where A1 and A2 are controlled by V count 1 and V count 2 respectively. The actual impedance, the actual implementation is in fact quite simple, since V out 1 is equals to RD ID1 minus RD ID2 and V out 2 is equals to RD ID4 minus RD ID3. We have V out 1 plus V out 2 is equals to RD ID1 plus ID4 minus RD ID2 plus ID3. Thus rather than add V out 1 and V out 2, we simply short the corresponding drain terminals to the sum the currents and subsequently generate the output voltage. Figure B. Note that if I1 is equals to 0 and V out is equals to plus GMRD V in and if I2 is equals to 0, then V out is equals to minus GMRD V in. For I1 and I2, for I1 is equals to I2, the gain drops to 0. In the circuit of figure B, V count 1 and V count 2 must vary V1 and V2 in opposite directions such that the gain of the amplifier changes more monotonically. Hot circuit can vary two currents in opposite directions. A differential pair provides such characteristic, leading to the topology of figure C. Note that for a large mod V count 1 minus V count 2, all of the tail current is steered to one of the top differential pairs, and the gain from V in to V out is at its most positive and most negative value. For V count 1 is equals to V count 2, the gain is 0. For simplicity, we redraw the circuit as shown in figure. D, called the Gilbert Cell. Is circuit widely used in any analog and communication systems. In a typical design, M1 minus M4 are identical, and so are M5 and M6. As with a cascade structure, the Gilbert cell consumes a greater voltage headroom than a simple differential pair does. This is because the two differential pairs M1 minus M2 and M3 minus M4 are stocked on top of the controlled differential pair. To understand this point, suppose the differential input V in figure D has common mode level VCM in, and VA is equals to VB is equals to VCM in minus GS1, and where M1 and M4 are assumed identical for M5 and M6 to operate in saturation. The CM level of VCM count must be such that VCM count less than or equal to VCM in minus VGS1 plus VTH5 6. Since VGS1 minus VTH5 6 is roughly equal to 1 over drive voltage, we conclude that the control CM level must be lower than the input CM level by at least this value. In arriving at the Gilbert cell topology, we opted to vary the gain of the differential pair. We opted to vary the gain of each differential pair through its tail current, thereby applying the control voltage to the bottom pair and the input signal to the top pairs. Interestingly, the order can be exchanged while still obtaining a VGA, illustrated in figure A. The idea is to convert input voltage to current by means of M5 and M6 and route the current through M1 minus M4 to the output nodes. If, as shown in figure B, V count is very positive, then only M1 and M2 are on, and V out is equals to GM M5 6 RD V in. Similarly, if V count is very negative, figure C, then only M3 and M4 are on, and V out is equals to minus GM 5 6 RD V in. If the differential control voltage is 0, then V out equals 0. The input differential pair may incorporate regeneration to provide a linear voltage to current conversion. Here you can see the figure A. Gilbert cell sensing the input voltage by bottom differential pair. B. Signal path for very positive V count. C. Signal path for very negative V count. Thank you.